Mario once again, and in this video I'm going to be explaining the timing that takes place in a typical navigation lights for RC model airplanes. This may not be exactly as the timing on the full-scale airplanes, but for model airplane applications it works just fine. And there are a number of ways that you can do these things with various circuits. In this particular video I am using a 555 timer and a decade counter, the 4017, very popular IC chip for these types of circuits. So I have seen many videos of people doing these things over the years, and I have never come across somebody that explains the the timing, or that has shown a timing diagram along with the circuits. Most of them just show you the LEDs blinking, as I've done myself, but in this video I'm going to cover a little more in depth, and I'm going to show you the timing diagram, that the way that I approach this particular circuit in what I was trying to achieve here. Now, if you look at the, you can go online and search for timing schematics for full-scale aircraft, and it'll give you the timing diagrams for the full-scale aircraft. If you know how to search those things, they're not easy to find. Depending on what words you use, you're not going to find that off the bat. So you have to kind of search for that information. But it's out there. Still, it was easier before. Now it's a little more difficult for some reason. The timing that okay. So let me show you the timing diagram actually on this on my sketch pad here. So this is what takes place, or what you want it to take place. If we look at the these LEDs, the way they're blinking, and I have several circuits here, so it's a little bit, maybe a little bit congested, but basically I have the same thing here. I have a 555 timer here with specific components. I have another 555 timer right here with specific components. This one is actually triggering this this board right here. And the lighting sequence is a little bit different on this one here. And then I was looking at that and I go, you know what, let me go back and revisit my timing diagram. And sure enough, there are a couple of things that are switched here. So we won't pay attention to this guy here. This is the one that I'm going to be explaining here. And this approximates more the strobe sequence and lighting that takes place on a typical aircraft lighting system. And so this one is connected actually to that 555 timer pulse generator. So I'm going to explain here what's happening here with these lights here. So if you notice the lights here, if I were to slow down my rate here, and the reason I did two types of 555 timer circuits here is because I was trying to get one that I could slow it down with the components or speed it up. This one actually is a little bit faster. I switched the capacitor here on this one, so it'll give me a little faster response here. But you can see that. So what's taking place here is this LED right here, which let's call it, for the sake of naming convention, A, B, and C, or B, C, D. Let's put it that way, BCD, because the A's are going to be your typical red and green that are on the wingtips of the aircraft or airplane that remain constant all the time, and they don't blink. So those would be the A in this particular example. So I'm going to be describing them also with the timing diagram. So those remain on all the time, and these are the ones that blink. So these would be the ones for the B would be white LEDs, and I'm only using one here, but you can double up on these for each side of the wing. This would be the wingtip, the rear trailing edge of the wingtips, or wingtip strobes. This would be the tail strobe, and this would be the beacon that typically sits way on the aircraft, top and bottom. Like I said, you can double up on these LEDs. I'm just showing one LED here for the sake of just the timing sequence. So if we were to look at the timing diagram of this sequence here, you're going to see something to this effect here. And I have referenced here to this pulse to these pulses here that are uh, referring to the output of the 4017. So if we were to look at the 4017 chip, we notice that it has 10, actually 10 outputs, but we're not using all 10 of them. And the more important ones are the what I have labeled here: Q0, Q2, Q1, basically Q0, Q1, Q2, Q3, but they're arranged in a certain way so that we can get the doubling up of the pulses on one LED. I could double up the pulses on the second LED, this white LED, but I'm not doing that because the effect is just fine the way it is. You can see how effective that looks, and it keeps the circuit very, very simple. Now, I'm not going directly from the outputs of the 4017 because when you do that, the LEDs become a little bit dull. You're not using the full intensity of the LED, and so I am using external circuits here to some transistors and capacitors, to amplify it and give it, more than anything, give it that strobe effect, that bing, that thing that goes on and off, and that's due to the capacitor and resistor combination that is associated with these transistors circuits. And so that's what's giving it that effect there, and as you can see, it's working out really nice. So the timing diagram, once again, is I have set up here, and as I was saying, I have a little sketch of an airplane there. And you can see the A, I've designated that to be the red and green typical markers that are on the aircraft on all the time. By the way, I am using a single LiPo with these circuits, so these run at 4.2 maximum or 4 voltage DC average. That is typical of a 1S LiPo battery. You can see how bright these things are at that 1S voltage, which is great for the little airplanes that I build these things for. You can go higher with the voltage, definitely, but in order to do that, I would have to change the resistors that are associated, the current limiting resistors that are associated with each of these LEDs, and I'll show you that in the circuit in just a minute here. So what we have is we have this timing diagram. It's like I was saying, we have let me grab my pencil here. We have the A, which are the red and green. So red is on all the time. So I have this mark that's full on, and full on the green plus VCC. In this case, like I said, is 4 volts DC. The B designation is for the strobes at the trailing edge of the wingtips, and those are the B designations. So what I'm doing here is I'm strobing at outputs of Q0 and Q2. I'm skipping the 1 here because I want that delay. Otherwise, it would just show as the LED full on for these 2 consecutive pulses here. So I'm kind of breaking that pulse rate, by skipping this trigger here from the 4017 Q output Q1, which would be the second pulse, because this is a decade counter. So it's a ripple counter, so it counts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. And so I'm using those outputs, as my trigger points for the to trigger to establish the timing diagram for these LEDs. And so I have the whites here coming on when Q0 turns on, skips 1, and when Q2 turns on, it feeds it back to that white LED, and that's what you're seeing here, the effect of that, the 2 pulses here, 1, 2. But before it gets to the second pulse, this light comes on here, which is the rear strobe for the tail light. And that's what I'm showing here in this diagram. So before it gets to the second pulse, this one comes out at Q1. And after that, after those 2 have sequenced, the beacon comes on. So you can see the timing is is per this setup right here. So here comes the red beacon. So these are beacons, and once again these can be doubled up, two per for the wingtip strobes. The rear one is typically just one strobe at the back of the tail end of the aircraft, and then D, which is the red beacon, that typically gets mounted on a full scale airplane, top and bottom. Because I'm going to be mounting these on my ultralights, I don't require the dual beacon here, the red, but I do require the dual white strobes at the back of the wingtips. So that's what I'm showing here. It's a very simple, very simple timing diagram. And there are other ways to do this. Like I said, there are so many people that have done these things in various ways. You can program these things on microchips using an Arduino board, to program it. I mean, there's so many ways to do this, but this is the way I have been doing these things. And the reason I explained in one other video, I have been doing this with these bulky components by today's standards, is because I have a bunch of these devices that I bought back in the 80s, and I wanted to make use of these components, like these potentiometers. You see, these are, I mean, they have these little tiny potentiometers that I could be using, but I have so many of these things that I have so many transistors, and that's the reason why I'm also using transistors. I have so many IC chips, counters, logic circuits, and that I've acquired over the years for projects of this nature. But I never really got really heavy into those things. I was heavily into electronic circuitry back, music circuits back in the 80s. When I was buying these things, I used to go to fairs, electronic fairs, and buy these things. From people who used to sell these by quantities, large quantities. So I used to buy them in bulk. Because it was cheaper to buy it that way, and because I don't want to go back and search for one particular item. If I had the urge to build something, in the early hours of the morning. So I have a bunch of those circuits. But basically, getting back to the circuit here, that's how simple this is right here. So translating this timing diagram into this, we can see the Q outputs here, and these are related in with electronic components here. So Q0, like I said, Q0, I'm skipping Q1 because I want that spacing there for the double flash on LED B, or LEDs B, which would be the white strobes for the wings, and I'm showing that here. So that's triggering both of these diodes. And you need diodes there, as your drivers, to do this kind of blinking here. That they're going directly into a 33 microfarad capacitor. The positive side is connected to the base of that transistor. These are NPN transistors, and then the output of that transistor is connected to an LED with a current limiting resistor of 150 ohms. And once again, if I were to use higher voltages here, this would have to change, because the current limiting has to be, the resistor has to be a little bit higher if you're going to use higher voltage here, just so that you don't burn out the LED. But because I'm using a low voltage here, 150 works just fine, and it keeps the LEDs nice and bright. But all that can be figured out by the specifications of the particular LEDs, because not all color LEDs have the same specifications. So some work at some consume a little more current, some consume less current, and they require different resistors. But for this application, I mean, I experimented with all that stuff, and for simplicity, I just decided to keep all the resistors the same here. So I'm using 150 for all these resistors, including the ones that are connected directly to V plus and ground, which are the ones that remain on, the green and red LED on the wing. Moving on to the second transistor here, that's turning on the C light, which would be the white rear strobe. And you can see I only require here the output of Q1 here to give me that effect. because as soon as this one kicks in right after it, and then it comes back to this one, and then it goes on to the red one here. So what I just said, it's explained right here. This comes on, then this is the C comes on, then this comes on again, and then the red comes on. So that's what I'm showing here with the Q1. So Q1 is directly connected to in other words, the C circuit is connected to Q1 output, and then likewise with the D, which would be the red strobe, you only need because I'm only using one blink, one pulse, for both the C and the D. These can be connected directly to the outputs of this 4017, as I'm showing in this circuit here. This is just a 555 timer circuit that I have it set up as to give me that variation in pulses here, and I can adjust that potentiometer, that 10K potentiometer. It has its own pulse, LED there. I can adjust that to, come on, baby. I can adjust that, so it'll give me slower. That's as slow as a rate right there, which is which would be about average. But if we want to increase that, it can, and that's the maximum right there. That's way too much. But about midway on that potentiometer would be about. Actually, it's a little bit closer to one extreme of the potentiometer. Right there. And you can adjust that, to your liking, because not everybody is the same. I kind of like that rate. And so, yeah, this is the circuit. This is the circuit diagram that I'm using. And once again, there are so many ways to do this. You can use different values here for different frequencies or pulse rates. But this is the way I have set up my circuit here, and to give me this particular timing diagram, pulse rates for each of these connections here, to the aircraft. And again, I have not seen anybody explain this. I wish somebody would had explained this, to people. I mean, I already knew this a while back, but I thought I'd do a video explain this, because I've never seen a video of someone explaining this, to this detail right here. And it's really simple. Once you understand what's going on here with the timing diagram, you can pretty much do any type of sequencing of lights, using these components here, the 4017. The other circuits that I've been showing here, I'm using a 4060 counter, binary counter, and that counter has an internal oscillator, so you don't need this circuit here. All you need with that chip, the 4060, is a the 4060. All you need is a capacitor and a couple of resistors, to establish the timing, the clock pulsing, and then so you don't need these bulky components here. Like I said, I could use surface-mounted components to keep the circuits very compact, or programming a chip would be a lot more compact. But this does not require code programming, and if you have components like that, like I have acquired over the years, you can make yourself a circuit like this. Now that you have this information here, if you understand, like I said, this is not hard to understand. It's just where do you want the flickering, the pulsing to take effect, and basically just adjust to your liking. But basically, this is what I would call a typical and very very true to the effect of full scale navigation lights. Mario once again with MIM Microflight. Any comments, put them in the comments below. If you care to comment, if you don't care to comment, at least give me a thumbs up, so that I can continue making these videos. It does it does inspire me to make more videos. I mean, I'm still going to make videos regardless, but it's nice, when I hear people talk about these things. If you don't like something, if I made a mistake, point it out. Uh, there's no wrong and no right in doing that. But it is nice when people not only give me a thumbs up, but also comment. Thank you for watching.